Okay guys, in this video we're going to be using our product quotient power rules to both expand and compress logarithmic expressions. And so we're going to start with expansion here and starting by defining what our product quotient and power rules are. And so one thing that I want to bring up here is essentially this. Remember that a logarithm, it is an exponent. And so what we're really doing is using these properties of exponents that we learned, say, in algebra class, like, hey, when I multiply two things with the same basis, what I do with the exponents? Well, I add the exponents together. That would be the natural thing to do here. And if I were to divide two things having the same basis here, we would subtract their exponents. Because of the fact that logarithms are exponents, we use similar properties here when we talk about products and quotients. And so what I want you to understand is that this logarithm being an exponent, we would say that two things here being multiplied together and having the same base, you can see base b right there. Let me see if I can write on top of this. Okay. Fix this guy really quickly here and bring it to the front. All right. No, not yet. Let's try this again. That's better. Okay. So because we have the same base here, we're multiplying two things having the same base, then really what we get is adding the exponents. But the way we write this is, well, the first exponent, log base b of x, plus the log base b of y. So without going into the rigorous definition of how we arrive at this, basically what we're seeing is multiplying two things with the same basis causes us to add our exponents. And dividing two things having the same base here, then what we're going to end up with is log base b of x, which is minus log base b of y, which is our quotient rule here. So we can rewrite products or logs of products as a sum of two logs, and we could expand quotients or a log of a quotient into a difference of two logs. Now our last rule here is our power rule. And power rule, generally speaking in algebra, we say a power to a power. When you raise an exponent to another power, what do we do with the exponents? Well, we multiply these things. And so because we're taking the log of something being raised to a power, and the log is itself a power, we're going to see that this n right here, we actually we throw it out in front like this. We say log base b of x. We're going to multiply it by n there. So what I want to do is I actually want to use these three properties to expand these four expressions that you've got right here, keeping in mind that when we expand, we have an order that we tend to like to go through here. So number one, when we expand, we always look for quotients first. If we have an overall overarching quotient. The second thing we're going to look for are products, okay? And then we tend to, lastly, look for powers. Okay, so when we look at this, we're essentially taking a log that has either a product or a quotient or a power inside of it and rewriting it as an expanded form of itself using a sum or a difference or a product. And so looking at this, letter G here, we say, well, which of our properties do I see going on here? Do I see any quotients on the inside of my log? Now, I don't see any quotients in here, but do I see any products? Well, I definitely see products. Just to point these out, I don't normally do this, but I'm actually going to write a dot for every single one of these products here because what that's going to imply is that we're going to rewrite this as the sum of a bunch of natural logs, but instead of having dots here or a product, we're going to have a sum. Okay. So in this case, we would say that this would expand, and to expand, we would see that it's the natural log of the first thing in the product, which in this case is just our x, plus now, instead of our multiply, the natural log of the second thing in the product, which is y. Now another product would imply plus the natural log of the third thing in the product, which is z squared. Now the question is, are we done? Now you'll always know whether or not you're done by looking inside of all of your logs and asking yourself this question, this series of questions. Do I see any quotients? Do I see any products? Do I see any powers? So in this first log here, I see the log of just x. That cannot be expanded anymore. We just say it's just a natural log of x. Here, also for the same reason, I don't see any quotients, powers, products in here, so we have the natural log of y. But over here, I see that we have a power. And so using my power rule, I know that I can just go throw that out in front. I would end up with this. Now, I know I'm done when I cannot expand any further, or that is to say when I look in all of my logs, arguments, and none of them have quotients, products, or powers. Excuse me. So as we look at these next three here, look a little bit more complicated. In this one, we're taking the natural log of z times z minus 2 squared. And so what I want you to notice is that we indeed have a product here. We just don't explicitly write a dot. But because I do have a product here, using my product rule, I'm going to rewrite this as log with the same base of the first thing in the product plus log with the same base of the second thing in the product where I have these two terms in my product. So what we end up with is ln of z plus now ln of, well, I suppose we'd have z minus 2 squared. So what we get is this. Now I notice that here I no longer have any quotients, powers, products, powers. Over here, this difference doesn't bother me. So that is to say, I can't do anything with it. But I don't see any quotients, I don't see any products, but I certainly do see a power. And so what we're going to want to do is throw that power in front. This is going to give us an expanded form, ln z plus 2 times the ln of z minus 2 here. So this would be completely expanded, and I can tell you this by looking at each of these here. We have something that's not having a quotient, excuse me, not having a product and not having a power. So now looking at letter K, now there's something I want to talk about with letter K. We have our rational exponent rule here. So let's talk about radicals and rational exponents. I want to make sure that you have this written down somewhere, but it's going to be the expectation that if we ever get a radical, we would say that, say we take the nth root of x to the mth power. We could actually rewrite this as x to the m over n power, where m is actually the power we're taking the inner stuff, or the radicand, to, and n is the root that we're taking here. So for instance, if I were to have something like x squared third root of this, that would be the same thing as x to the 2 over 3 power. Now, the reason why I bring this up is because if we're going to be dealing with properties of exponents, then anytime with logarithms that we see a radical, we're going to rewrite it so that it has a rational exponent. So instead of the log or the natural log of the cube root of x over y, like this, what I'm going to say is that because I have x over y technically to the first, but we're taking the cube root of that, we could really rewrite this as x over y to the 1/3, which would mean the same thing as the first power third root, or just the cube root of this. So looking at this now, sorry, I didn't mean to write equals there, I meant to have a parenthesis. The natural log of x over y to the 1/3 power. We get this here. I'm actually going to suggest that we take this power down here first. And so because I have a power, we can bring this out in front. I get 1/3 the natural log of x over y. And looking in here, because we see a quotient, this would mean we're going to need to rewrite this as a difference. Now the interesting thing here is that 1/3 was a cube root, and that cube root applies to both the x and the y. So when I write this time, I'm actually going to expand my quotient inside of here. I'm going to say the natural log of the top thing, which is x, minus the natural log of the denominator thing, which is y. You can see that the 1/3 will apply to both of these here. And so one thing I can tell you is this would be considered to be an expanded form, because we don't have any quotients, powers, products, quotients, powers, products in here. But what we could do also is say, distribute the 1/3 and say it's 1/3 ln x minus 1/3 the ln of y. And putting this back together, you could see that putting the powers back on both of these, the 1/3 back up on our x and our y, that would satisfy that we were taking the cube root of both of those. But however you choose to write it, you would have to make sure you apply the 1/3 to both of those terms. Okay. So let's take a look at letter m here. We have the natural log of some quotient, it looks like here. And so our quotient rule says, hey, you know, we'll just rewrite this as log base b of the stuff on top minus log base b of the stuff on bottom. Well, we have log base e, and we're saying log base e of the stuff on top, which is x squared minus 1, minus log base e, or natural log of the stuff on bottom. Now, can I do anything with this? Now, I want to recognize something here. We can't do anything with this power because it's inside the argument here. And we would have to be raising everything inside the power to that. If the 2 had been outside here, then I could have put it out in front. But because the 2's in there, we have to leave this. So this has no quotients, no products, no powers. So I'm going to leave this natural log term here. But over here, this natural log term, I notice that we have a power there. We should rightfully place this out in front. So we have the natural log of x squared minus 1 minus 3 times the natural log of x. And now we can see that we've completely gotten rid of any quotients, products, or powers. Cheers.